Okay, so today we're going to be talking about early warning system that UNHCR is developing along with the Luxembourg Institute of Science and Technology. Today, UNHCR identifies 16 countries worldwide which are ranked high risk of new or escalating emergencies driven by external events such as conflict or climate shocks. Where both likelihood and impact are high, these situations are expected to trigger significant displacement and rising humanitarian needs that exceed our current response capacity. So these countries are identified through horizon scanning and risk analysis, and they're internally applicable to UNHCR. So to support these timely emergency preparedness and proactive response, we are developing an early warning system to anticipate when, where, and how many people may be displaced with the aim of saving lives. So what are the expected impact? So displacement forecasting help us move from reacting to crisis to preparing for them. And by anticipating shocks, we can strengthen community resilience so people are better able to withstand, adapt to, and recover from disruptions while also reducing public health risks through improved preparedness. And it also ensures that affected populations can access timely, adequate, and equitable essential services. And this not only meets urgent needs, but also improves protection for the most vulnerable, ultimately reducing mortality and harm. Lastly, forecasting enables early data-driven action. And with earlier funding, pre-positioning of supplies, and surge capacity, we can respond faster, deliver services more quickly, and coordinate more effectively, making better use of limited humanitarian resources. So how does this frame look like? Displacement risk is at the intersection of the three key factors: hazard, vulnerability, and exposure. So firstly, hazards are the shocks themselves, which would cause displacement. And secondly, exposure refers to the people and infrastructure in the path of these hazards. And lastly, the vulnerability captures how susceptible those populations are based on factors such as poverty, access to services, existing fragility. When these three elements overlap, displacement risk emerges. And then these three data sets, sets of data sets will be ingested into the machine learning models, and the outputs will be visualized in a web-based platform. So for our prototype, we selected flood-induced internal displacement in Somalia. It's because of a few reasons. So UNHCR and Norwegian Refugee Council have been collecting detailed internal displacement data sets since 2016 through Protection and Solution Monitoring Network, which is available publicly. Somalia is cyclically affected by floods, affecting population, and there are compounding displacement drivers in Somalia. So this was a good example to take as a pilot country. So through our analysis, first analysis, we found some characteristics of flood-induced displacement that we found. So first finding is that for flood-induced displacement, people do not move before the flooding happens. So there's no pre-event departure, and the displacement starts really rapidly 24 hours of flood onset. And the second finding is that from departure to arrival, travel is not a long distance. It's a very short distance, and it typically takes less than 48 hours by land. The third finding is that once flood recedes, people return. People do not tend to stay where they are, and the displacement is extremely short term. For our models that we ingested around 15 types of data sets from hazard, exposure, and vulnerability.
Um, So to follow, my name is Thanh Nguyen, and I'm delighted to be with you all today. And would like to share some of the results that we have made on behalf of UNHCR and the Luxembourg Institute of Science and Technology. In order to undertake this project, we rely on available resources and also state-of-the-art resources such as the global flood awareness system, GLOFAST. On the left-hand side, you can see an example of the stream flow medium to extended range forecast up to 30 days. And on the right-hand side, those are the Sentinel-1 derived flood extent maps in bare soil and urban area that list carried out within the Global Flood Monitoring System project. Can you go to the next slide, please? So here I would like just to mention one of the variables from the table that Azuka shared earlier. Here to generate the flood depth variable, we combine GLOFAST stream flow forecast with global flood hazard maps from the JRC. And this is a typical method like the one proposed by Klimada. Next, please. Thank you. So let us compare the performance of the different regression machine learning mode and machine learning models used for this displacement forecasting on the basis of those variables. The evaluation focused on two key matrices, R square, which measure how well the model explains variability in displacement outcome, and RMSE, root mean square error, which measure prediction error. Among other approaches, the three main ones are XGBoost, random forest, and TAP-BFN. Across these experiments, all models achieve relatively similar performance levels, but TAP-BFN show the strongest overall result, suggesting that it capture displacement patterns slightly better than the others. These results are, sorry, and not yet. These results are encouraging, but at the same time, the moderate R-square values also highlight that the displacement dynamic remain highly complex and influenced by multiple interacting factors beyond the environmental variables alone. Next slide, please. Yes, thank you. So this slide this slide is to present the experimental result of the displacement forecasting model together with the explainability analysis used to better understand the model behavior. On the left-hand side, we compare the predicted displacement values against the observed displacement values using a loss function. The observed displacement values are the one from the PSMN protection and solution monitoring network that Azuka mentioned earlier. Here, the gray vertical range represent the 5% to 95% quantile prediction intervals in order to provide an estimate of uncertainties around each prediction and how decision makers understand the confidence range of the forecast. One important observation is that the model tend to overestimate smaller displacement event below 100 and underestimate very large displacement event be above 5,000 people. And this reflects the inherent difficulty of modeling highly nonlinear and extreme humanitarian events. On the right-hand side, we want to present the shape-based prediction explanation to identify which variables contribute the most strongly to the model predictions. And this is a step forward, explainable AI and transparent operational forecasting. The results of the analysis show that temporal indicators such as weak number, environmental variables like precipitation, soil moisture, and flood fractions are among the most significant to displacement prediction. Next slide, please. So here, it show additional experimental result focus on the classification of this displacement event magnitudes. On the left, the histogram illustrate the distribution of the distribution of internally displaced person events in the dataset. We can see that the dataset is highly imbalanced and heavily skewed towards small displacement events, particularly events with fewer than 1,000 displacement people. Large-scale events are comparatively rare, which create an important challenge for machine learning models. So to make the forecast more operationally relevant, we categorize the displacement event into several ranges based on the humanitarian thresholds. Yes, thank you. So maybe we can, yes, so here is fine. So a couple of challenge to summary, the displacement forecasting require a combination of multiple type of expertise and data source, including humanitarian, environmental monitoring, socioeconomic analysis, and humanitarian field action, field information. We one of the major challenges is the data scarcity, particularly for conflict and violence related displacement. The data qualities is another critical issue, especially for internal displacement population record and variation in reporting standard, delay reporting, and missing information can directly affect the model reliability. Another challenge is the causal complexity, where the displacement is rarely driven by a single factor. So generalization across regions is also a key limitation, where the models trained in one country or one context may not perform equally well in other region or other contexts.
Dan, thank you so much. Yeah.
Thank you.